So for next Monday, the 5.4.526 of your textbook, these are on the rigid body, so is what we are going to do today and tomorrow and on Friday. So, and then I'll give you 2 problems today. So these 4 problems for next Monday. Should I wait? Somebody still? Is somebody still around, or two people? Okay, let's start then. Should we wait? Any questions about what we have done last week? Because now we move to the next subject, that is the motion of the rigid body. Well, actually, the kinematics of rigid body. Well, let's start from the kinematics, right? Kinematics means there are no forces. Then the dynamics is when you put in the forces, okay? And hello. So what is the rigid body? Well, you can guess. I mean, this table roughly is a rigid body. It's just a collection of points that the distance among these points are fixed. Okay, so if you have a collection of n points, clearly this system has a large number of degrees of freedom. But if you fix the relative distances among these points, the number of degrees of freedom is much less. Okay, we already sort of discussed these things. That is, if I take the chalk, this is made of a large number of atoms that you can think as points. But clearly the number of degrees of freedom of these chalks is not very large, because in fact how many coordinates I'm supposed to fix in order to completely give the position of this chalk in the room? Not 10 to the 23 or whatever Avogadro numbers, but just think of the, first of course you have to think of the center of a mass, so that gives you 3 coordinates. Then, having fixed that, the chalk can still rotate, right, 3 ways, so you need to give 3 additional angles or generalized coordinates. So actually the number of degrees, this is true for any rigid body, I mean big or small, it's only 6, okay? You only need 6 coordinates to fix the position of a rigid body. There are many ways to understand that. I think the simplest one is the one I just said. Another way is maybe you see if you fix the position of 3 points, not a line, in a body, then essentially you have fixed the position of the body. You see that? Close your eyes. If you have a body like this, if you fix the position of 3 points in this body, of course, if they are aligned, this is not true, because then you can still rotate. But if they are arbitrary 3 points, then you have fixed the position of this body. Okay? So 3 points, how many degrees of freedom? 9, right? It's 3 times the number. Each point 3. You have 3 points, 3 by 3. But so why not? So why did I say 6? But you see, there are 9s, but then remember this is a rigid body, so the relative distances among the 3 points are fixed. Okay, so it's 9 minus 3, and it's magic 6. Okay, so degrees of freedom for a rigid body is 6. Okay, so you have many ways you can get this result that you only need 6 generalized coordinates. And now, again, there are not just 6 coordinates arbitrary, because 3 of them, I said, they are the center of the mass coordinates, okay? And those are not so interesting, right? Because, well, they are interesting, but those are as if you take all the mass of the body and you compress it to a point, right, that is the center of the mass, and then that point moves under the effect, under the action of the external forces. Okay, but there we are not going to learn anything new, because we already know how a point of whatever mass moves under the action of external forces. So we are back to F equal ma, or the Lagrangian of a single point, okay? So clearly the new physics has to do with the geometrical distribution of the mass, to the fact that this is not a point, is an extended object, albeit a rigid body. And so the interesting kinematics and then the interesting dynamics has to do with the rotational degrees of freedom, okay? So in a way, you have 6 degrees of freedom, but 3 of those are those of the center of the mass, okay, it's something that we already know about. So we are going to concentrate about what is the kinematics of the other 3 degrees of freedom, okay? So one way to discuss this is you have your set of axes for a frame of references, and here you have your rigid body. And the usual way, you have to tell me how this body is oriented in space, right? So one possibility is that you give me another set of axes, orthogonal axes. Okay, so this is, you can call it big X, usually, I guess, X, Y, and Z. And this is little x, little y, little z. So if you give me the position and the orientation of this new set of coordinates, okay, of axes, with respect to another set of axes that you think outside the body, that specify the position of the rigid body, okay? You see that, right? You take the chalk, you put something fixed on the chalk with 3 axes, then the relative position of this new set of axes with respect to some arbitrary set of axes defined at rest, so to speak, in the room, that gives you the position of your rigid body. And so the origin of this new set of axes is, you put it in the center of the mass of the rigid body, and that is 3 of these 6 coordinates. And then the relative orientation of these axes are going to give you the new generalized coordinates relative to the other 3 degrees of freedom, okay? So here again, you have a large number of possibility, because what you are saying is what is the orientation of one set of axes with respect to a new one. And probably you are familiar with this, direction cosines, maybe, I don't know, have you, that if you have 2 sets, so you take this, so we agreed that 3 has to do with the center of the mass, so I just take this and I bring it back here, right? I can always do this by translation, and then these angles here between the axes are called the direction, well, the cosines of these angles are called the cosine, the direction cosines, okay? Have you ever seen that? Yes? No? Okay. That's not very important. In fact, we are not going to use this definition, but you see, it's just a linear algebra. I mean, just go back to how do you define a rotation, right? Because that's what we are discussing. We are discussing, we factorize out the center of a mass motion, okay? It's not interesting. I mean, it is interesting, but we already spent some time on that. So now we concentrate on the rotational motion of the rigid body. So essentially we have to describe rotations. And that you know how to describe, I think, right? They are matrices. And how do you describe that? Well, one possibility is as this set of axes is rotating with respect to the original one, you give me the new angles by which each of these axes has rotated with respect to the original one. And so if you now introduce, so how do you define angles in space? Well, an angle is defined by two vectors, right? So if you attach, that's the usual way you do this kind of things. In fact, I think usually x is here and y is here, right? So this is y prime and this is x prime. So if this is z, this is z prime. So you put these unit vectors meaning a vector that has a length of some of 1 in some units, right? And so this is the usually I is for the x direction and j for the y direction and k. So these are unit vectors. So that means that if you take the square, right, this or the modulus, whatever, these are equal to 1. But because you are defining a set of axes, they are also orthogonal, right? Meaning that if you take I dot j, this is equal to I dot k, that is equal to, I guess, j dot k, and they are equal to 0, right? That defines an orthogonal set of unit vectors. In other words, you are defining your orthogonal axis for your coordinates, and then you rotate, right? You rotate. So you go to a I prime, you go to a j prime, you go to a k prime. These are still orthogonal, with norm 1, but they are rotated. And so you see that you are defining angles. For instance, you define, I don't know, for instance, this angle here between, so let's call it 1, 1, this is defined by this, right? You take the scalar product of these two. Because their norms are equal to 1, this is exactly this angle. You see, you can define 9 of these because you know all the possibility. So I don't know, you have a cosine 2, I guess, is j prime. You can keep on going, right? Cosine 3 is the same with the k. But then you also have you have more, right? Like 1, 2, 1, j, something like this, and you can make 9, but they are not all linearly independent, clearly, because only 3 must be linearly independent, because after all, you only have 3 degrees of freedom. And you see, these are 9, but then you have 6 conditions from the fact that they are norm 1 and orthogonal. So from 9 minus 6, you're back to 3. That is the number of degrees of freedom. So this. Okay, so this is the usual way. And you see that the way to describe this is through, so if you define now the component of a vector here, right, you see that those are transformed by a matrix to the new component with respect to the new set of coordinates, right? This you must know from your linear algebra, that if the component of a vector after a rotation of your set of coordinates right, they change according to this rule. Where these are matrices, okay, these are the element of a matrix, 1, 1, I don't know, 1, 2, 1, 3, and so on and so forth. But it's not an arbitrary matrix, as you know. I mean, it's not just an arbitrary matrix. It's a special matrix that has the important property of being orthogonal. That has to do with this. And also, the determinant should be 1, right? You remember the definition. So in the matrix language, that means orthogonal means that if you take the matrix times the inverse matrix, and the inverse matrix is just the transpose matrix. Do you remember that? Right, this is the definition of orthogonal matrix. And actually, this is, because of this condition, is an orthogonal matrix that has determinant equal to 1. So the problem of describing the rotation of a rigid body, you see, boils down to the problem of describing rotation in general. And that's good because that, again, is a problem that you have already solved in terms of these matrices. Any rotation can be described by orthogonal matrix with determinant equal to 1. And this is a group, right? Here, it's a group, right? SO3. So it's O3, and then special because of.
So why do you label those data 3 and 1, 1? They are all equal, I think.
Why I call it 1, 1?
Yeah, I mean all are equal. So why not?
What you mean? They are equal? They're not equal.
1, 1.
It's not equal to cos. It's not equal to theta 2, 2. I mean, it depends on the rotation, right?
Yeah, you rotate the coordinates. So
No, but it can be squeezed, right? These are not necessarily.
okay.
I mean, at least 3 of the. No, they are different. They are equal if you rotate like this, right? Then you have 2 that are equal and 1 that is 0. But as soon as it's skew, you have 3. In fact, these are the. But we are not going to use. I mean, in a second, I will introduce another set of angles that are more. Well, in a way, they are nicer, and they are the one that we are going to use as generalized coordinates. But let's first finish this. Notice that you always have a sort of dual interpretation of this, because I said these are the change in coordinates of a vector under a change of axis, right? But you can always think of that as you keep the axis fixed and you rotate the vector, right? You see that it's just one is the opposite of the other. I mean, you have a vector here, and if you rotate your axis according to this rule, the components of this vector change according to this multiplication, given the rotational matrix. But you can always think of the dual picture in which the set of axes remains fixed and the vector is rotating. It's just one, the opposite. It's not the opposite, but it's the active and passive way of describing the rotation. Is this clear? Or if you have a vector like this, and I rotate the vector, right? Then I'm changing the coordinate with respect to the axis given by the sides of these 3 walls, right? Because I'm rotating. This is a rotation. But the same, just with the opposite sign, it's taking place if I keep the vector fixed and I change the walls of this room, right? So you always have these 2 pictures, okay? And that really, yeah.
What's active and passive picture?
Well, it depends on what. Usually, active means that the vector is moving. And passive, the vector is fixed, but you are changing your description. You are rotating in a way. That, by the way, is the reason why we introduce vectors, right? Vectors are nice because the vector is invariant under this transformation, you understand? A vector is just a vector, right? And it's just described by this. And it just happened that many physical quantities are vectors. If you wish, this is a discovery, right? There are things in the world that are scalar. A scalar is something that remains the same no matter what rotation you apply to your set of coordinates, okay? And you see that around us there are quantities that are scalars. For instance, the temperature in this room, in each point of this room, doesn't change if I rotate the room, I guess. So temperature is a scalar quantity. But if I have a vector that is identified by my arm, okay, if you rotate the room, you take the components of my arm in this new rotated room, that changes. And it changes according to this rule. That defines a vector in 3 dimensions, okay? And you can keep going. I mean, there are many things that are vectors, like velocity, the acceleration, the force, I mean, you know. And then you keep going. There are more complicated objects that are called tensors that transform with similar rules, but with more indices, right? And in the world, there are things that are tensors. You understand? Like stress, it's a thing that has many components. It cannot be described by just 3 components. Stress, you know, and so on and so forth. So what are examples of rotations? Well, the simplest example is clearly let's just stick to the blackboard. So it's a rotation in the plane, right? If you have, you were about to ask something, or no? I heard some. No, I just. So let me stick to 2 dimensions on the plane because, as usual, it's easy. You see, it's easy to draw. And as I said, you have a rotation. So what is the matrix describing? So this is the simplest rotation that you have a x and y that goes to x prime. You have just one angle in this case. That's nice. That you call phi. Okay, this is a particular case of the general rotation that we describe by these orthogonal matrices, and you know, I hope this rotation, you see, is described by the well-known matrix right? This is the 2 by 2 matrix describing this. And what should I put here? Well, nothing is taking place in the 3rd direction, so I just put a 1 and then some zeros. And you can verify that indeed the inverse matrix of this is just the transpose, right? The transpose, you take the column, you put them as rows, and if you take that, you multiply by the transpose, by definition, you get 1. And also the determinant you can verify very easily, right? Because you get the cos square plus sine square, so you get also that the determinant is u1 is 1. So it does belong to the SO3 group. Okay, so how about rotation in 3 dimensions? Because after all, we don't want our bodies to be constrained in 2 dimensions. A rigid body naturally rotates in 3 dimensions. Okay, so as I said, this set of angles is not very nice, and so people, well, it's not very nice because you have 9 and they are not linearly independent. Okay, so you really want 3 angles so that you can identify those angles as your generalized coordinates. Okay, generalized coordinates must be independent. And so people introduce other sets of angles to describe rotations. And there are many sets, But okay, we discussed only one of these. And this is due to Euler, a mathematician of, I think, the 1800s. So they are called Eulers. So the kinematics of a rigid body is based on this, how do you write Euler? Euler's angles. So these are like the x, y, and z for the kinematics of a rigid body. So I have to introduce this angle. So let me try. This is always confusing because I have to describe a rotation in 3 dimensions by drawing on a 2-dimensional blackboard. But okay, so I start. So you see, to define the angles, essentially I start from a given, as I said, a given set of axes. Okay, so they are orthogonal axes, and this is x, y, and z, and through 3 rotations, each of which describes an angle, I go to an arbitrarily rotated final set of axes. Okay, because of what I said up to this point, this will define a rotation. So let's do it in 3 steps. So step 1. So maybe I should go this way. That is. So first angle, so I start from x, y, and z. Now I rotate about the z-axis, okay? So I take this and I rotate up. So I end up, so this remains the same, and I call it now theta. And I rotate by an angle. You see, I'm rotating, well, these two should be the same, by this angle that I call phi. Okay, is this clear? So you have, you rotate in this about, so it's a rotation. You keep fixed the z-axis. Now you call it theta. This you call it eta, and this you call it xi, or psi, depending. So this way you learn more Greek letters. That is always nice. Step 2, so now this is not the most general rotation, clearly. This is one rotation. Now I do another rotation. So now I'm in this set. So now I do another rotation. Let's see if I can get it. So you start now from, sorry, now you are in this position. So like this is like this, right? And this is like this. Okay. So now I want to rotate about, you see, this axis psi that was the x. Now I rotate about this one. So this remains the same. And I rotate by an angle theta about this axis. So this guy that was the same before, okay, goes to another axis by an angle theta, right? And the same, this one goes up here. So this now is eta prime, and this, I guess, is theta prime. So like this, now about this, third step and third angle, I do a final rotation about this axis now. It's again like this axis, but now is the rotated one. So I start from here. Let's see if I can get it. Okay, and now I rotate here. And this is my, so this is my z prime, the final axis that is equal, because I'm rotating about itself, is equal to theta prime. Now this one, so I'm rotating this way, so this one goes up by an angle that I call psi. And this is now the y prime, and this is my x prime. Or if maybe it's better like this. So I'm rotating like this, so this goes to side, this goes with. So phi, theta, and psi, these are the Euler angles. So if you are completely confused at this point, I don't blame you, because it's always confusing, but it's just the fact that our brain does not work in 3 dimensions. I mean, you have to face this fact. It's a fact of life. Is the reason why we use mathematics. Okay? It's very hard to visualize 3 dimensions, but all you need to know, or all you need to take from this is that is just a definition of 3 angles that you see. This is a completely rotated new x, y, and z prime system that is a complete rotation starting from x, y, z, and x, y, and z, the original set. Okay, and you just did it in 3 steps. Each of these steps defines an angle, okay? And these are the 3 Euler angles. Clearly, you can have different definitions. You can pick the one you prefer, but because all textbooks and most of the physics of the rigid body is discussed in terms of the Euler angles, I suggest you adopt the same conventions, okay? So now we have the generalized coordinates to describe a rotation, okay? And so what is the matrix? So before here, I wrote down the matrix for a general 2-dimensional rotation, right? That you already knew. The natural question is, what is the matrix for a general rotation in 3 dimensions, right? That's what we need. So it's going to be a matrix that it will depend on these 3 coordinates. But what is this matrix? So if you so look at probably a much better picture of this you find in the Goldstein books. Okay, it's draw much better. So if there you can maybe understand more clearly the definition of these Euler's angles. Now. This was geometry, but again, actually, it's much easier to work with the linear algebra, and so we want this the matrix A. We want the matrix A of a general rotation, and the way to find this matrix A is to go back to each individual rotation and write the matrix. And then you compose these 3 rotations by multiplying the matrices, and the product of these 3 matrices is going to be this matrix that describes the whole motion. And so what I have is the product of 3 matrices that I call B, C, D, where D is the matrix of the first rotation. So what was the first rotation? Okay, you have forgot by now what was the first rotation, but it was a rotation that was by keeping, so it was a rotation in the plane. In what plane? In the xy plane, right? Because I kept the z. So that you already know is the one that we wrote before, right? So far that's easy. Right, because this was, you remember, was this rotation about this axis. So it was exactly a rotation in a plane. They are all rotation in a plane. The only question is what plane. And here the plane clearly, I keep is about the z direction, so it's xy. So it must be this, right? Because this is x, this is y, this is the z direction. How about C, the matrix C? Remember, the matrix C was the one in which I rotated about this axis, right? And that is the x-axis. So this is a rotation about the x-axis. So you see, the axis that remains the same is the 1, 0, 0. So now it's 1, 0, 0, 0, 0. and the cosine sine things are in here. So the only thing is have to remember that now I'm talking about theta, not phi. So I have sine theta minus sine theta cosine theta, right? So this matrix describes a rotation about the x axis. This about the z, and so dCB. What is the matrix B? Well, if you remember, that was again a rotation about the z-axis, albeit the final z-axis, not the original one. But that doesn't. We don't care about this. Still, is about the z. So it's exactly like the first one. Only thing is that now I'm talking about psi and not phi. So this must be the matrix. And so I'm almost done. And the only thing is, unfortunately, I have to multiply 3 matrices. That requires some energy. So so I'm not going to do that in real time. I just write the result. Maybe if you, over the weekend, you check. So the result of this is a 3 by 3 matrix that unfortunately is rather complicated. And so can I erase this? Yeah. So the final result of this matrix, that is the product of the 3 matrices that I just wrote, is, well, you find it in any book, but let's write it in all its glory. So this is just the 1-1 entry. Okay. So 1-1, 1-2, 1-3. Okay. And well, you know that it is complicated because each time you multiply a matrix, you have to take a row and multiply by the column, right? So that generates a lot of terms. But okay, never mind. So this is 2-1 element. This is the 2-2. And finally, the last row is just sine theta sine phi minus sine theta cos phi and cosine theta. Okay, not that bad. So that's the matrix that describes, in terms of the Euler angles, a general rotation, okay, by that amount. Okay. So that's the basic structure that enters the kinematics of a rigid body. Then I guess one should, so let's formalize what I said at the beginning. The general displacement of a rigid body is going to be, so if you take one point fixed in this rigid body, then the most general displacement, you understand, is a rotation about some axis, okay? If you let that fixed point to move, then you have the most general displacement of a rigid body is a translation plus a rotation, okay? Is where we start. These two things, they even have a name. The first is called the Euler's theorem, the same Euler who introduced the angles, and the other is called the Charles theorem, but that's just in case you read somewhere these names, then you know what they are. Okay. So now I want to discuss before we discuss the full problem of the dynamics of the rigid body. Let's just focus on rotations and point out a very simple things that maybe I already told you about. The interesting things about, you see, rotations are described by matrices. And you know that in general, matrices do not commute. Oh, that's the interesting thing. You know, numbers commute because 2 by 3 is equal to 3 by 2. But matrices in general, I mean, except very special matrices, do not commute. That if you multiply the A matrix by B, for instance, if you invert the order of this, you get a completely different matrix. Now, how come that rotations do not, I mean, can be described by matrices? Because maybe you are used to the fact that the classical world, everything commutes, that you do not commute only in quantum mechanics, right? You met this idea of not commuting when you start studying quantum mechanics, but actually it's very easy now, right, to understand that rotation do not commute. That is, the order in which you perform a rotation influence the final position of the body. Think my hand. First I rotate this way, then I rotate this way, and I end up with my hand facing that way. But so first, that. If I do the opposite, right, I end up in a different position. You understand? So the order of which you perform your rotations, that is the order of these matrices, change the final position of your body. So if you change the order, you end up with a different rotation. So you don't have to go to quantum mechanics to see that in the physical world there are quantities, operation, which depend on the ordering. Is this clear? Or? So rotations are very interesting because you see they have all these features that you may think are very remote. You need quantum effects on this kind, but no. I mean, even a rotation has this effect that you must be careful when you take one after the other, right? Because the order of your rotations change the final position of your body. So that's the reason why you need matrices to describe rotations. Otherwise, it would be enough to have vectors or scalars, right? So that's the connection between physics and mathematics. If the physics is such that, for instance, like a rotation, do not commute, that the ordering is important, then you cannot use vectors or scalar quantities to describe rotations, because those quantities, right, do not have this feature that they do not commute. So you really need matrices to describe rotations. Okay, so that's the first thing I want to stress. And the second one, that is just that is just the opposite of what I just said, is that as long as the rotations are infinitesimal, they do commute. And that allows us to use vectors to describe infinitesimal rotations. Okay, so that's the next. So in general, for a finite rotation, you have to use a matrix. And that's complicated. So before we do that, before we worry about the full matrix, let's just consider infinitesimal matrices. And for those, it's easy to show. You see, if you write an infinitesimal matrix, so the general rotational matrix is these things, if I write it in terms of the Euler's angle. But if I think this as an infinitesimal rotation, meaning that is a rotation that is given, so the full matrix is just the identity matrix, 1, 1, 1, and then just an infinitesimal change about this unit matrix. So I call it epsilon because it's small. Okay, it's a matrix. This epsilon, you can verify. It has three so it has just let me call it d omega 3, d omega 2, and d omega 1, and it is symmetric, anti-symmetric. Sorry. So I'm writing, to understand this, you just take this matrix and do an expansion, okay, for small rotational angles about the unit matrix. If you do that, you will see that you have one on the diagonal, and this is the one of the unit matrix. So that's just a matrix that does not do anything, no rotation. So you end up with the same set of axes, and then just a small. So all these angles are infinitesimal, okay, small. And I call them the omega 1, 2, and 3. In that case, you end up with a matrix that is in this form. And you see this is a particular matrix because it's anti-symmetric. So to specify this matrix, I only need 3 components. Right? It's a 3 by 3 anti-symmetric matrix. And because it's anti-symmetric, by definition, you must have 0 on the diagonal. So instead of having 1, 2, 3, 4, 5, 6 components, okay, you just have 3. But if this object is characterized by only 3 numbers, that means I can think of this matrix as a vector in 3 dimensions, right? So that means that this rotation, that is an infinitesimal rotation, can be characterized by a vector that I guess I call the omega vector, that has as component the infinitesimal angles that are some function of my Euler's angles. D omega 1, d omega 2, d omega 3. So that means that as long as my rotation is infinitesimal, then I can characterize that by simple vector. That's very good because a vector is much simpler than a matrix. And in fact, we already used this when we were describing rotation at the beginning to describe the conservation of the angular momentum, because the infinitesimal change of a vector r, for instance, the position, right? Like, under the action of a rotation, you remember that was something like this, where this was this rotational angle that is really a vector. So to draw this, you remember this is a vector product. So you want these vectors that describe the rotation points this way. And then if you have an infinitesimal rotation of your vector r, so this is r, and this is the right. So this is the new r prime, and this is the infinitesimal dr prime. So dr prime is defined this way, where this angle, right? This is theta, and this is d omega. So you see, I can describe the change of my vector under this rotation, and I don't need a matrix. I only need a vector that is defined in this way. Okay? Now, why I'm doing this? Why is it useful to have a description in terms? So let's put it another way. Why is it interesting to look into infinitesimal rotations? After all, well, clearly it is interesting because if I'm doing derivatives, right? If I want to study the derivative of a vector, all I need is under the effect of a rotation, all I need is an infinitesimal rotation, because derivatives are defined on infinitesimally small quantities. So that definition of a rotation that is good and sound, as long as I'm talking about infinitesimal rotation, can be used to define the effect of a rotation on the derivative of a vector. So let's do that. And in a second, you will see why this leads to a number of problems that are interesting. So so that you know. So let's step back for a second and ask ourselves, what is the rate of change of a vector, an arbitrary vector that I call G? So rate of change of a vector. So I'm talking about an infinitesimal change of a vector, arbitrary vector that I call big G. Okay. Okay, that's you take essentially this is the differential, so it has to do with the derivative. If you take the change in time, you take a time derivative of this, right? But I want to do something a little more subtle. I want to study the rate of change of a vector when this vector is defined on a body, okay, that is rotating. And you see, this is a very relevant question because it's our case. All the vectors that I'm defining in this room with my arms, actually I'm defining them on a rotating body that is our planet. So this is a very relevant question. How I describe the change of a vector that is not only changing because it's changing because of some force, but is also changing because the frame of references is rotating. Okay? And therefore, by what I said, this is going to be made of two parts. One is simply the change of this vector as I measure that on the body that is rotating. So this is due to some force, something that is changing my vectors. But there is also a component that I call, I guess, dg rotation, that even if I'm not doing anything to this vector, the simple fact that our planet is rotating is changing that vector, right? With respect to an observer who's staying outside the planet. It's clear, right? If I'm pointing like this, I'm not doing anything. But if you are standing on the sun, you see me rotating, not as slowly, actually, because in 24 hours, I go around 360 degrees, right? But even if I'm not doing anything, so this is this part here of the change, and this is the part that is changing because some force is moving these vectors, okay? So you see where I'm leading, because this is what I wrote there, right? This is simply the omega vector cross G. This is just a change of this vector because of this gigantic rotation of my frame of references. And this I don't know. This you have to tell me what is the force, and I will tell you what is the change of this. No, because now this is this active-passive things. Here I was changing the vector, but it's a good question. But now I'm thinking that the vector is just staying there, and I'm changing my frame of reference. So there is a minus. I repeat. Is this, I mean, as I said before, you can think of a vector, right? If the vector is moving, then this was the definition of the rotation. But you can think of the vector as standing there, and you are moving the set of axes instead. And you see that is the opposite. There is a minus sign in this case, because in one case it's rotating like this. In the other case, the set of axes are rotating, so it's like if had rotated. And this is the second case, right? Because here the Earth is rotating and the vector is standing. So I take the opposite sign. And so this is a general change, differential change, but general. So if I specify that I want to study the change in time, so you may call this space if you want. So maybe this is easy. This is as measured on the body, on the rotating body. This is the change measuring space, meaning stepping out from the rotating body. And so you have to compensate for the rotation, so you have to add the rotation. So if I take a time derivative, for instance, then I have the general rule that the change in time of a vector in space is equal to the change of your vector in time as measured on the body, plus this term here, okay, where I'm considering only the change in time of this, right, because this will be a second order effect. So I have here d omega dt, okay, but this is what I call d omega, is the change in angle in time. This is the angular velocity that usually is called omega. So in other words, omega is d omega dt. So, but you see that now we are doing something, we are moving out from, so this is the basic formula. This is a very useful formula because for any vector, it tells you how the change of that vector in space, in time and in space, is related to the change of that vector on the body, okay? And you see that we are moving out from what we have said up to this point, because remember the first day we said we are going to discuss problems in inertial frame of references. And I remind you that if inertial frame of reference is a frame of reference that is either at rest with respect to something or is moving with constant velocity, okay? But now we are not talking any longer just of that system, because now we are talking about frames of references that are rotating. And that is not at rest and is not moving with constant velocity, right? It's not just a translation, it's accelerating, because something that rotates accelerates, right? So you see, this formula allows us to ask questions that we were not allowed to ask up to today. Because up to today, if you ask me what happens if I'm on a car which is accelerating, I wouldn't know, because it's beyond the scope of classical mechanics as defined for Galilean frame of references, right? If you have an acceleration, either you put that in as an external force or you don't know what to do, right? But here is exactly what the tool you need to describe a system that is rotating, like the Earth. And so finally, we are in the position to answer the question I asked you at the beginning, is how do we know? How do we know, in fact, that the Earth is rotating? We said that you cannot say that because you are saying the sun and the stars rotating, because that is a kinematical problem. You may as well say that either we are rotating and they are fixed, or vice versa. They are rotating and we are fixed. Nothing changes. Nothing changes. But so how do we know, in fact, that we are rotating? And now we have a tool, because if we are rotating, when we take the derivative of a vector, we are not going to see just this term. We must see also this term, right? If we are rotating. If we are not rotating, this is 0, and 0 times anything is still 0, and so we will see only this. So we are, if the Earth is rotating, we must start seeing effects. For instance, this could be a force, right? This could be some acceleration, and we will see some extra terms in the force that do not come from external forces, are just there by magic, right? So a system in a rotating system, even if you have this term equal to 0, that doesn't mean that this is different from is 0 as well. So there are two kinds of effects, and I leave those as two exercises. So are the two problems that I wrote here that you are supposed to solve in addition to the. So we discuss those next Monday, and what are these two? I think you don't need. Maybe I should spell out a little more. Otherwise, you have a horrible weekend in solving. So let me just spell out some more details. So I said, let's take this this G to be. You see that if I start computing, let's say I want to compute the velocity of a point mass using this formula, right? So you see that if I compute the velocity, I have the velocity. Let me call this space. I put S. Okay. So this velocity is going to be the velocity I measure. So let me call it V sub B, right? But because now I'm not at rest. I'm not in a Galilean frame of reference, an inertial frame of reference. I have to also put this term here, right? So I have omega cross what? This is the velocity. That means that the big G in this case is the position, right? Because so here I have to put the position of this. Now, if I have the velocity, the next thing to try is now I want to compute the force, so I need the acceleration. Now, the acceleration is what? Is the derivative, the time derivative of the velocity, right? But wait a moment. It's not only this, because I'm still rotating, so my acceleration is going to be that derivative plus omega cross Vs now, right? Huh? V. VB.
S is dVB by dt plus.
No, it's still G, right? It's the G that I'm measuring. So it's Vs. I'm measuring. So what is this? So this. So this is on the body,
Yeah.
and this. So what is the? So this, the first term is just Vs on the body. So this is by definition is just the acceleration as measured on the body. Then I have. So I'm plugging in this, okay? So take this and plug it in. So the first term is just this. Then you have this term that you have to take the derivative. This is constant. We are just assuming that the body is rotating, but with constant angular velocity. So I have a term. So that is omega cross. So I take the derivative. So this is V body, okay, the first term. Then you see that I have to take this and put it here. So I have one term that is just the same as this. So actually I have two of these. And then I have this that is a omega cross R. Okay, you have two terms. One comes from here, one comes from plugging this in here. So you have twice omega cross VB, Then you have omega cross r. So if you multiply by the mass, this formula, then okay, then you have, so let's multiply by the mass. You have a mass. So if I multiply an acceleration by the mass, I have the force. And so you see I can write, now let's take, let's say we want to compute the effective force, the force that you perceive on the body. So in a way, I'm taking this one here, right? So I take the terms on the other side. So it is the force that you measure in space. That is the force that you measure if you didn't have any rotation, right? Minus these two terms. So minus 2m omega cross the velocity on the body, the velocity as measured in the body, minus m, this other term that is omega cross r. So what I'm saying is that if you measure the net force on a point particles on the body, that is our case, we measure actually the force on a point particle here, on the Earth that is rotating. Then I get the same force that I would measure if the body was not rotating, that is in space, right, from outside the body, minus these two terms. So even if you have zero force, still because you are measuring the motion of this particle in a rotating body, you have two extra terms. These two extra terms, well, this I guess you already knew, is called the centrifugal force. This you are familiar that, say, if you are on a merry-go-round, you know, this thing that rotates, right? You know that you experience the force, right? It's if it rotates very fast, it's very hard to stay on the things because you tend to be pushed away, right? In fact, you know that the further away from the rotational center you are, the stronger is this force. Okay, you are familiar with this? I mean, there are many. So if you are on a disk that is rotating and you are here, there is a substantial force that is throwing you away, right? And if you can think of that as the same. If you rotate a ball attached to a line like this, right? It rotates. And the line connecting the balls is each time acting and compensating this centrifugal force, right? That would tend to toss the ball away. Okay, so this is a familiar term. You already knew about that. This maybe you didn't, or maybe you did, I don't know. This is called the Coriolis, another French guy, force or effect. This is a little less trivial in the sense, you see, this tells you that this force, the centrifugal force, is clearly proportional to the angular velocity, in fact, to the square of the angular velocity. So the faster the merry-go-round turns, the stronger is this force. And also, the further away from the center, that is the larger r, the larger is the force. This one is a little bit more complicated in the sense that it's proportional to the velocity. So as long as you do not move, there is zero Coriolis force. But as soon as you start moving, then you have a component that is called the Coriolis force that is acting on you just because you are in a frame that is rotating. Okay? Did you know about that? You did. Everybody knew? Well, now you do. So, having said that, I can tell you about the problems. So the first problem is simple. Of course, you can also write a Lagrangian if you wish. You could think, I'm not doing that, but you find this in the Landau's books, that is the other textbook I suggested. You can write the Lagrangian for a point particle in a non-inertial frame of references. And clearly, you are going to have some extra terms that must take into account the centrifugal and the Coriolis force. But that I leave you to. I leave it to your. So the first problem. Now that you know this, that was contained in this equation, you can solve two problems. The first one is the interesting problem that what happens if you drop something from a tower? Okay, this was one of the first questions that were so when Galilei and this guy say, well, the Earth is rotating, no? That's not clear. The first thing they said, okay, if the Earth is rotating and I drop something, right? Because in the time the things falls to the ground, the Earth has rotated a little bit. In fact, has rotated in this way, so this thing should fall not I don't know, on my feet, but a little west of my head. Because, well, here, let's say a very high tower, I drop it, so it takes, I don't know, 5, 6 seconds. In 6 seconds, the Earth has rotated a little bit. So this is going to fall a little bit west of what I drop it, they say. Okay. Actually, this clearly is not what happened, because you know that because of the, if this in first approximation, essentially it should fall exactly down there, because the thing is rotating with the Earth when I hold it, so it has a small component also in that direction, right? It's not, and so that component is exactly right to balance what the things would lose with respect to the Earth while falling. However, there are those two components. They didn't know about that. So I want you to compute. So first problem, find. So answer this. This was an objection that was raised. So find deflection. Find deflection of freely falling body. So take a point mass from vertical, so drop it, caused by the Earth rotation. Okay, so you are in a very high tower, or maybe not even, well, yeah, okay. So I give you also some numbers. So so solve the problem. Okay, and then plug in the numbers. So it's going to depend on how high this is. So for a tower of 100 meters, a skyscraper. Okay. So estimate this deviation, but also more importantly, the direction of this deviation. Is that west or east of your position? And you'll be surprised, because it's exactly the opposite. You may expect this to go west because the Earth is rotating, but actually there you are wrong, because it has this component of the velocity. The net deviation is east, and is due to the Coriolis force. Very small. It's a few centimeters here, but you will find out. So do this exercise. So that's already proof, because you find this small deviation eastward, that already proved that the Earth is rotating. But this is not the way originally it was proved. It was proved in another way, and this is the second problem. And so this was problem number 1. Free falling from h equal 100 meters. So problem number 2. This is called the Foucault, another French guy. They are all. That's all the fault of the French Revolution. The Foucault's pendulum. So this is a pendulum. However, this pendulum is allowed to oscillate in any directions. Okay, there is a very big one is in Paris. Where is it? Do you know where? Maybe. No, you say yes, yes, or maybe. Do you know in Paris there is? Yeah. Well, I don't know because you say yes, yes. So I thought, you know about the pendulum. Yeah. Okay. Somewhere there is one very big pendulum. I think it's in Paris. And this place where people like to do that experiment we already talked, that you take the pendulum, 1 inch from your nose, and then you drop it. This is a big sphere of heavy metal, and it goes all the room, like 20 meters, and then comes back, and people scream because they think it's... but of course, because of energy conservation, they cannot be hurt. But this is not what you want to measure here. There is a very peculiar thing that this pendulum is oscillating, and it doesn't keep on the plane. I mean, up to now, we have learned that essentially, if you have a pendulum, then that is oscillating, it keeps oscillating in a fixed plane, right? All the exercises we have done, we didn't consider the three-dimensional problem. It was just 1 degree of freedom because it was keeping oscillating. This is true, but it's true in space. If the body or the frame of reference you are computing, again you have this Coriolis force, right? And remember, the Coriolis force is a vector product, so it's a tricky thing because if you have a velocity going here, you have a force that goes orthogonal to the velocity. So you understand that if you have a pendulum on the Earth, this pendulum, the plane of the pendulum, is going to rotate over the 24 hours, right? There is a very intuitive way to understand that. Go to the North Pole, okay, and then oscillate. You step out from the Earth, right? I know it's not possible, but assume you are hovering on top of the North Pole with the pendulum. You are in space, so the plane of this pendulum is fixed, but the Earth is rotating under the pendulum. So the polar bear looking at the pendulum on the Earth will see the plane of the pendulum rotating completely by 360 degrees after 24 hours. This effect is taken into account by the Foucault. The Foucault is the pendulum, the Coriolis force. So I want you to compute this fact. You have to solve the equation for a pendulum, but allowing for the 3 dimensions. And you are going to get components of a force from the Coriolis force that if you take those into account, you will see that the plane of the pendulum goes around. Of course, it goes around, and it goes around. Let's do it right. It depends on the longitude of your position, right? Because on the North Pole, it goes around in 24 hours, but Trieste is not on the North Pole. The longitude of Trieste is roughly 43 degrees, right? If you ever wondered. And so take this into account. And you will find out that it goes around roughly in 40 hours. instead of 24. So it takes longer. So this is actually, you remember, this is really the way people knew that the Earth rotates. They took a pendulum and they waited and they saw that. That there is no explanation, except if you are in a frame of reference that is not inertial. So that means the Earth rotates. That's the proof. So if somebody tells you it's not true, it's the sun that is rotating, well, you just show this pendulum. Okay, it takes 40 hours, but at the end, he must be, or she must be convinced. Okay, so these two problems, we solved them together on Monday, and now we are ready to discuss the dynamics of the rigid body, but that we do on Friday. So I just want to mention another interesting effect of the Coriolis force, just for your general. There is another so you see that in everyday life this is not a very important force because it's very tiny. It depends on the velocity, but there is a place where it's very important, and is about wind. You know wind, like the borer. Now, wind moves from places where there is a from high to low pressure, right? If you have high pressure and low pressure, and so if you think of the Earth, right? I have here sort of if you look at the northern hemisphere, right? So it's something like this. And in general, I mean, on the average, of course, high and low pressures, they change with time. But on the average, if this is west and this is east, right, you expect to have low pressure higher north, right? And roughly at the tropics, you have high pressure. Okay, here is warmer, so here is cooler, so. So you expect the wind to go this way, right? So in the Atlantic, you'd expect just a very strong wind going parallel to the coast. So that would be very, well, in a way convenient if you have the right wind, sails, right? But this is not what you know that the wind goes like this. It bends. The prevailing winds, they go like this in the northern hemisphere. So why is this? This is, again, is the effect of the Coriolis force. If you think of the air moving, like in the wind, this has a velocity, and on this mass of air, you have a Coriolis force. And the Coriolis force tends to bend the winds. That's the reason why winds go like this, and the opposite in the other hemisphere. So that's another place where you see this application of the Coriolis force. Okay, so that's kind of interesting too. So on a very large scale, there it's a tiny effect. It's a small effect, but it accumulates, right? Because it all the way from the tropics up, then it keep on acting. So eventually the wind tends to bend. Then of course you have all sort of local perturbations. So it's not like this. It's more complicated, but the general average of this is about this, okay?